Welcome to another video. So in our today's discussion, we're going to discuss biomolecules and cells 2017. Question 1 reads, choose the correct statement. Option 1, which says, an atomic orbital can have a maximum number of 2 shares. An atomic orbital can have a maximum number of 2 shares. So that to some way sounds to be a true statement. So let's first list the atomic orbitals that we have. So we have got the S, we have the P, we have D and F. Okay, so the S atomic orbital has got only a single orbital. Okay, then the P has got 3, 1, 2, 3. Then D has got 5, F has got 7, or these atomic orbitals. So each single atomic orbital can only be filled up with a maximum of 2 electrons. That is, this one, it's a 4 there. This one also can only be like that. So each of these atomic orbitals can only be filled up with a maximum of 2 electrons. So an atomic orbital can have a maximum of 2 shells. Okay, so I didn't read this statement carefully. So as you can see here, it's saying shells. So here it was supposed to be saying electrons. So it's a false statement. 2 is saying an atomic shell can have a maximum of 2 atomic orbitals. This is false. 3 is saying the second atomic shell can have a maximum of 8 electrons. The second atomic shell can have a maximum of 8 electrons. This to some way sounds to be true, because if we consider the electronic configuration, we always say 2, 8, then comma whatever. So the second shell will be considered to be full if it has got 8 electrons. So that to some extent is somehow correct. Then 4 is saying the first atomic shell can be occupied by a maximum of 3 orbitals. So this is false. The first shell can only have, it only has got an S atomic orbital, and this S atomic orbital only has got a single orbital. This single orbital can only be filled up with a maximum of 2 electrons. So that is, the first atomic shell can only be filled up with a maximum of 2 electrons, because it has got a single orbital, atomic orbital. Then 5 is saying the S orbital has higher energy than the P orbital in the same shell. So that is false. So let's consider the second shell. In the second shell, we have the 2s and the 2p. So even the arrangement on how these are drawn here, you'll find that it is the same energy level, but 2p is at a higher energy level as compared to the 2s, despite both of them being in the second energy level. So the 2p has got high energy level as compared to the 2s in the same sublevel, in the same atomic subshell. So the opposite is true. The S orbital has higher energy than the p orbital in the same level. So the opposite is true. It's supposed to read the p has got high energy than the S in the same atomic orbit, as you can see, because energy increases like that. So the correct answer here is going to be option 3, which is saying the second atomic shell can have a maximum of 8 electrons. That is a true statement. Question 2, which reads, choose the correct statement. The first atomic orbital to be filled by the electrons is the 1p. So this one is representing the number of shells. So this is the first shell. So in the first shell, we don't have p. The first shell only has got an s orbital. So we just have one s. There's no 1p or one d or one f. So there's only one s in the first shell. So that is false. 2 is saying the first 3 electrons in the p orbitals or the second shell will be unpaired. This is a true statement. So we said that the first 3 electrons in the p orbitals or the second shell. So the second shell, this is going to be 2p. This number in front is representing the shell you are in. So if we say 1s, it means this is the first shell. If we say 2s, it means this is the second shell. So if we say the 2p, this is the second shell. So we said that the p has got 3 orbitals. So 1, 2, 3. So this option is saying the first 3 electrons in the p orbitals of the second shell will be unpaired. That is true. So let's say you just have 3 electrons which you are supposed to fill them in this p orbital. So you follow the alpha-bow principle. So you start by filling 1 here and 1. So all the 3 are done. So they are unpaired. If let's say you had 5, you first start by filling 1 in each. Then from 5 you have 2. Then you come back and start again. So you would say 4, then 5. So on 1 would be unpaired in that case. So in this case, all the 3 are going to be unpaired. This is a true statement. Then 3 is saying the 1s atomic orbital can have a minimum of 2 protons. So this is a false statement. We are not talking about protons. Atomic orbitals deal with electrons. The function of neutrons is to neutralize electrons in the atom. So this is false. The function of neutrons is to contribute to the mass number of an atom. The hydrogen atom has 2 electrons in each shell. So the hydrogen atom, we know that hydrogen only got a single electron. So this single electron is filled in the first shell. So the hydrogen atom has only a single electron in each shell. It would have been a correct statement. So this is a false statement. So the only correct answer here is option 2. The first 3 electrons in the p orbitals of the second shell will be unpaired. That is true. 3. Determine the maximum number of electrons in the second shell of an atom. Determine the maximum number of electrons in the second shell of an atom. So this is just a repetition of what we have already explained. So we have been saying that the second shell is filled up with a maximum of 8 electrons. So the answer is 8 there. If you still have some extra electrons, you take them to the third energy or third shell. Determine the number of valence electrons in an atom with atomic number of 17. Determine the number of valence electrons. So I've always been saying that we have what we call the valence number and valence electrons. These two are not the same. Valence number. So valence number, this one is found in the number of electrons in the outermost shell. Now in a case where you have more than 4 electrons in the outermost shell, but they are less than 8, for you to find the valence number, you're going to say, let's say a particular atom has got 5 electrons in its outermost shell. We can't say the valence number of this atom is 5, no. So you're going to say 8 minus 5, so you're going to get 3. 3 is going to be the valence number for this particular atom. But the valence electrons, these are just total number of electrons in the outermost shell. So if you have a particular atom which has got 5 electrons in its outermost shell, and you're being asked to determine the valence electron, you just count how many electrons are in the outermost shell. So it's going to be 5. So that's the difference between valence number and valence electron. Whereas if an atom has got less than 4 electrons in its outermost shell, the valence electron number or the valence number is going to be those same number of electrons. So determine the number of valence electrons in an atom with an atomic number of 17. So I've got 17 atomic number. It means that 17 electrons. So electron configuration for this one is going to be 2, 8. So 2 plus 8, that is 10. For us to get 17, we are remaining with 7. So 7 is going to be the valence electrons. So we should get 7. But if this question was asking the valence number of this atom with a 17 atomic number, the answer was going to be 8 minus 7. So it was going to be 1. 1 was going to be the valence number. But valence electrons just count the number of electrons in the atom shell. So there we have 7 as our answer. Question 5. Choose the correct statement. Nitrogen gas contains 2 atoms linked together through covalent double bonds. Nitrogen gas contains 2 atoms linked together through covalent double bonds. So nitrogen has got 7 electrons. So the electronic configuration is going to be 2, 5. For this to become stable, it needs at least 3 electrons. It has to gain 3 electrons. So nitrogen gas is going to be this. It's linked together through a converter double bonds. So come. Water contains 1 oxygen atom linked to 2 hydrogen atoms through hydrogen bonds. So these, yeah, it's true. Water contains a single oxygen atom and 2 hydrogen atoms, but these are linked through a polar covalent bonds, not a hydrogen bond. Carbon dioxide has a carbon atom linked to 2 oxygen atoms through ionic bonds. Carbon dioxide is a CO2. As you can see here already, we have got 2 oxygen atoms and a single carbon atom. Has a carbon atom linked to 2 oxygen atoms, yes, through ionic bonds. So this is a covalent bond. It's not an ionic bond. There is no losing and gaining of electrons, but there is a sharing of electrons. So it's not an ionic bond, but covalent bond. For instance, sodium chloride contains sodium linked to chloride through an ionic bond. Yes, this is a true statement. So ionic bond, this is a type of bond which involves gaining and losing of electrons. So sodium chloride, which is common salt, we have got sodium, which is a metal. It loses an electron, and chlorine, which has got 7 electrons in its outermost shell, it gains that electron. So this one which loses, this one gains. This is what we call ionic bond. So this is a true statement. 5 is saying a hydrogen bond can only be formed between 2 water molecules. That is false. So hydrogen bond will be always formed when hydrogen is reacting with any of these highly electronegative atoms, which includes oxygen, nitrogen, and fluorine. When hydrogen is reacting with any of these highly electronegative atoms, the bond is what is known as hydrogen bond. So the correct statement here is option 4, which was saying sodium chloride contains sodium linked to a chloride through an ionic bond. So that is a true statement. Now option 2 was saying nitrogen gas contains 2 atoms linked together through a covalent bond. So if you look at this, you're going to have each of the nitrogen has got 5 electrons. So these 5, let's say 1, 2, then 3, 4, then say 5. 1, 2, 3, 4, then say 5. So 1, 2, 3, 4, 5, 6, 7. So you still need another one. They are supposed to be 3 for this to become stable. So it has to be triple covalent bond. And nitrogen gas contains 2 atoms, so they have to be 3. So nitrogen gas does not respect this. So the correct answer here anyway, it's going to be option 4. That is chemistry. A double covalent bond refers to a sharing of dash electrons. A double covalent bond refers to a sharing of. So if we say there's a double covalent bond, let's say like that one we see in carbon dioxide. So just consider this. This is a double covalent bond. So how many electrons are shared in this covalent bond? So what will happen here is that this carbon is giving out 2 electrons. Okay, oxygen is also sharing these 2 electrons. So together a double covalent bond is going to have a total of 4 electrons. So 2 from this atom, also 2 from the other atom. So the total is 4. So we are supposed to get 4. So a double covalent bond refers to a sharing of 4 electrons, whereas a single covalent bond like that one which we see in water, this bond you only have in this bond you only have got oxygen giving out 1, hydrogen also giving out 1. So this is a single covalent bond. So we have 2 electrons in a single covalent bond. The other 2 will come from this. It's another single covalent bond. So a double covalent bond you're going to have 4 electrons. A single covalent bond you're going to have 2. you're going to have 2 electrons. Question 7. In a water molecule, the non-bonding electrons in oxygen is or are. So in a water molecule, the non-bonding electrons in oxygen atom is or are. So we have this hydrogen reacting with oxygen to give us a water molecule H2O. So we understand that oxygen has got 8 electrons. Okay, has got atomic number of 8. So its electron configuration is going to be 2, 6. Okay, so we know that the electrons which take part in the chemical reaction are those in the outermost shell. So since we have got these 6 electrons, or the 6 electrons, we have 2 which take part in the chemical reaction. Since when I was showing this covalent bond of water, I said the 2 electrons come from, this hydrogen has got a single electron. Oxygen is going to give a single electron, to share a single electron with this hydrogen. The other electron from there will be shared with this oxygen. So all the 6, we can see that only 2 are going to take part in that bond formation. So how many are remaining? So from 6 minus 2, you are going to have 4. These 4 do not take part in the chemical reaction. And these 4 are the ones which bring about lone pairs. So these 4 are going to be in the atomic orbitals. So you're going to have this and that. The 4 are going to be like this. So there's going to be what is known as repulsion. This pair of electrons, what we call a lone pair. So you have a lone pair of electron, another lone pair. So in your water molecule, you have got 2 lone pairs. 1, 2. 2 lone pairs simply means that you have got 4 electrons. So this question is saying, in a water molecule, the non-bonding electrons in the oxygen is or are. So the non-bonding, those which do not take part in this bond formation, as we have seen, only 2 take part in the formation of water. So how many remain? These 4. These 4 do not take part in this bond formation. So the answer there is 4. And these are the ones which bring about, which gives water its bent shape, because there is repulsion. So initially water was supposed to have a linear structure. It was supposed to be hydrogen there, then oxygen, and another hydrogen here. Now, because of the presence of lone pairs on oxygen, these lone pairs repel each other, and they repel. There is this force. So this force is attributed towards hydrogen atoms, thereby forcing these hydrogen atoms to bend inward. So hydrogen will be here, another one will be there, bring about a bent shape of water, and this angle is approximately 104.5 degrees. So why we have that is because of these 4 electrons which do not take part in the bond formation of water. Hence they repel each other, thereby forcing hydrogen atoms to bend inwards, bring about the bent shape. So 4 electrons do not take part in the bond formation of water, whereas only 2 are involved in that bond formation. Which of the following statements describes a covalent bond between carbon and oxygen? So carbon and oxygen. So which of the following statements describes a covalent bond between carbon and oxygen? So we have carbon reacting with oxygen. We're going to have carbon monoxide. So the electrons are shared equally between carbon and oxygen atoms. So what we have here is that carbon dioxide has got 4 electrons in its outermost shell. For it to become stable, it needs 4. Oxygen has got 6 electrons in its outermost shell. For it to become stable, it has to gain 2. So what will happen is that we are going to have this, then carbon dioxide, which has 4, okay, like this, then this oxygen has got 6 in its outermost shell. So you are going to have, okay, like this. So carbon will not be stable again in this bonding. So which of the following statement describes a covalent bond in this case? So the electrons are shared equally between carbon and oxygen atoms, between carbon and oxygen atoms. So 1, 2, 3, 4, 5, 6. No. Electrons in the bond are closer to the carbon nucleus. So in this case, what you should know is that oxygen is highly electronegative as compared to carbon. As a result, electrons will be more close to the highly electronegative oxygen than carbon. So that is the first statement. 3 is saying each atom in the molecule keeps its electrons. No, so the electrons are shared. Electrons in the bond are closer to the oxygen nucleus. Yes, this is true. Why is that the case? Because oxygen is highly electronegative as compared to carbon. So electrons are attracted more towards the highly electronegative atom than the less electronegative atom. This is the same situation between hydrogen and oxygen in a water molecule. That is why we have partial charges in a water molecule. Then 5 is saying the electrons in the molecule are evenly distributed. That is equally distributed. So this is false. As you can see, oxygen is going to gain 2 from carbon. Then carbon, which has got 4, all these 4 have to be involved in the bond formation. It will be better off for you to understand this when you use carbon dioxide, because in carbon dioxide, this carbon is going to have 4 of its electrons involved in bond formation on either side. So the correct statement here is the one which is saying electrons in the bond are closer to the oxygen nucleus than the nucleus of carbon. The reason is because of electronegativity. Identify the correct description of hydrogen bond. So we said that hydrogen bond is a type of bond which is formed when hydrogen is reacting with any of these 3 highly electronegative atoms. So a bond between oxygen, hydrogen, and hydrogen atoms of the same water molecule, which correctly describes, that's the key word. 2 is saying a bond between oxygen of water and nitrogen of other molecules like ammonia. No, a bond between oxygen and hydrogen of different water molecules. Then a bond between 2 hydrogen atoms of different molecules. So option 2 and 3. So it has to be, if we are using water, it has to be a bond between hydrogen of one water molecule and oxygen or the other water molecule, like this. This bond here is what is known as hydrogen bond. So a bond between oxygen and hydrogen of different water molecules. Yes, this is true. What of option 2? A bond between oxygen of water and nitrogen of other molecules like ammonia. So it has to be the oxygen, the hydrogen of water and nitrogen of other water molecules such as ammonia. Hydrogen has to be involved in that bond formation, not just oxygen and nitrogen. No, this is not going to be a hydrogen bond, but hydrogen and nitrogen, this will be a hydrogen bond. So option 2 is the first statement. Therefore, the only correct statement here is option 3. It has to be a bond between oxygen and hydrogen of different water molecules, as I illustrated. Then choose the statement which distinguishes liquid water from ice. So what's the difference between liquid water and ice? One thing we should know is that ice is less dense as compared to liquid water. Why is that the case? It's because when water is frozen, it creates spaces which we call lattice. So those spaces bring about makes ice to be less dense as compared to liquid water. And also the volume of ice is greater or higher than the volume of liquid water. The reason is attributed because of those spaces which are created, they increase the volume. So that is what happens. Then also in ice water, each water molecule is linked to a maximum of 4 other water molecules. a maximum of 4 other water molecules. So why is that the case? That is simply because so my reference point is the water molecule which is at the center there. I want to illustrate what I mean by that. So this will be linked to that, this will also be linked to this, then we're going to have this linked to that, this also be linked to this. So each water molecule in ice water will be linked to a maximum of 4 electrons. So when this happens, the next one is also going to be linked to 4 electrons, thereby creating, there will be spaces. So choose a statement which distinguishes liquid water from ice. In liquid water, each molecule is surrounded by 4 other molecules in liquid water. Then in liquid water, molecules are more densely packed. This is true. This is true. In liquid water, molecules are more densely packed. There are no spaces there. Then in liquid water, the molecules are arranged in a regular pattern. In liquid water, the molecules are arranged in a regular pattern. So this is false. A regular pattern which we call lattice, that is only formed in ice. Then in ice, the hydrogen bonds between molecules constantly make and break. This is true for liquid water, not ice. In ice, the bonds are compact, they do not easily break. Then in liquid water, molecules are less densely packed. So this is true for ice. So what distinguishes liquid water from ice is going to be option 2. In liquid water, molecules are more densely packed. That is why liquid water is more dense as compared to ice. So option 1 was saying in liquid water, each molecule is surrounded by 4 other molecules. So this is true for ice. Option 1 is true for ice. In liquid water, it's possible that each water molecule can be linked just like this one here. You can see that it is only linked to a single water molecule. Okay, so this will be true for liquid water. But for ice, each water molecule is going to be linked to a maximum of 4 other water molecules. So the correct answer to this question is option 2. Then capillarity of water in a vessel depends on so capillarity, this has to deal with the absorption of water from the ground or from the soil all the way up to the branches and the leaves. Okay, so what brings or what makes water to be able to be pulled up the gravity, like from the ground up the ground? What brings about that? So one of the forces is that you need to have cohesive forces. So cohesive forces, we say that these are forces which exist between like molecules. So in that case, like molecules, water and water, they have to bond. That bonding is what we call cohesive forces. So in the first place, water have to stick to themselves, to each other. So you need cohesive forces. The other one now, you need adhesive forces. So adhesive forces, we say that these are forces which exist between unlike molecules. So unlike in this case, it's between water and the wall of the vessel. Wall of the vessel. So water also has to stick to the vessel wall. So for this water to stick to the vessel wall, the forces which have to exist there are what we call adhesive forces, because these are unlike molecules. Water and the vessel wall, they are not like. They are unlike molecules. So you also need this force. Then lastly, you need what is known as capillary action. Okay? When these two coexist, you are now then going to have capillary action. So water is sticking to themselves, adhesive forces. This water also has to stick to the wall of the vessel, adhesive forces. Then capillary action now will allow this water to move up the gravity. So capillarity of water in a vessel depends on adhesion, yes. Water's density properties, it does not contribute. Cohesion, so 1 and 3 are true. So 1 and 3 above. So the answer is going to be option 5. That's your answer. In capillary action, you need both cohesive and adhesive forces. The meniscus of water in a narrow tube. So the meniscus of water is that caved pattern that you see in a tube. So let's say a glass, you're going to observe something like this, okay? So this curve is what we call meniscus. So what brings about this meniscus? So what brings about this meniscus? One of them is cohesive forces. There are very strong cohesive forces between water molecules. So water are able to stick to each other through these strong forces. Now because they are able to stick to each other through strong forces, they are pulling themselves down. By them pulling themselves down, they create this meniscus. Okay? They create this meniscus, which is a curves upwards. Which curves is this? Upwards, yes. Then another force is there's also adhesive forces. So adhesive forces between the glass wall and the water themselves. But adhesive forces are weak as compared to cohesive forces, which bring about this meniscus. So the meniscus of water in a narrow tube curves upwards due to high cohesive forces between water molecules. Is flat, so it's not flat, it's curved. So this is force. Curves downwards due to cohesive forces between water molecules. Then it is flat, no, curves downwards due to adhesive, so it has to be cohesive forces. So now the question is, we are this kind of, so this is curving downward, okay, downward is like this, so it's upward, not downward. So it curves upwards due to high cohesive forces between water molecules. The answer has to be option 1. So it's because of cohesive forces, which are like forces that exist between water molecules. So these are very strong forces, so they are able to pull water down. As they pull water down, then water is able to create this curve, which we call the meniscus. So it's an upward curve, which is as a result of cohesive forces. Which one of the following statements is true about water? So hydrogen bonds are a result of electrical attraction between water molecules. Hydrogen bonds are a result of electrical attraction between water molecules. So electrical attraction. Electrical simply means electricity or electric field. Water is capable of sticking to the sides of the glass using cohesive. So we say that the forces that exist between water and the glass are adhesive. So cohesive exists between like molecules, which is not true. So glass and water are not like, they are different molecules, so it has to be adhesive, so it's false. Then water molecules form spheres on a polar surface. Water molecules form spheres on a polar surface. So polar is a charged surface. Then water is a polar molecule because the electrons on oxygen and hydrogen are equally shared. So they are not equally shared, they are unequal. That is what brings about polarity of water. So they are unequal. Then adhesive forces help water to stick together. So it is the cohesive forces which help water to stick together. So we have disqualified option 5, option 4, as well as option 2. So we're remaining with 1 and 3. So 1 was saying hydrogen bonds are a result of electrical attraction between water molecules. That is, these hydrogen bonds are able to exist because of electrical attraction between one water molecule to the other. So I would not support this statement because of this. That attraction is not electrical. Then 3 was saying water molecules form spheres on a polar surface. So polar surface, this is a charged surface. So water is going to form a sphere. Spheres, these circles like. So this is a true statement. It's because if you look at water, water has got two charges, positive and 2 negative charges on oxygen. So if you introduce water to a polar surface, what you're going to discover is that depending on the polarity of that surface, let's say if it's positively charged, those are going to be attracted to let's say they will be attracted to that. If they are negatively charged, they'll be attracted to this, thereby forming a sphere. Okay, so I would go with option 3. Okay, question 14. Which one of the following statement is not true about water? When water boils, covalent bonds are broken. So that is the first statement. So these covalent bonds exist within a water molecule. But one water molecule to the other, these are linked through what is known as hydrogen bond. So this will be linked to that. This bond is what we call hydrogen bond between one water molecule and the other. So if you boil water, the bonds that break are these ones, the hydrogen bonds. That is why we show them in dotted form. These are covalent bonds. Covalent bonds are very strong, so they do not break. Okay? So what breaks are hydrogen bonds. So when water boils, covalent bonds break. That is the first statement. Water molecules are hydrophilic. Water molecules are hydrophilic. So something hydrophilic is water loving. So this is a true statement. Water molecules like water molecules. So they are hydrophilic, they are water loving. Then a water molecule is not linear. This is a true statement. Water is not linear. As you have seen, this is a bent shape. I've already explained on how this shape comes about and the approximate size of this angle. Then water is an excellent solvent for polar substances. That is true. So a solvent is something that is able to dissolve other molecules. So water is able to dissolve polar, which are charged substances, because of its polarity. Water has a very high latent heat of vaporization. You need a lot of heat energy for you to vaporize water or to change it from liquid to gas. That is also a true statement. So which of the following statement is not true about water? It's option 1. When water boils, covalent bonds are broken. So this is the first statement. So covalent bonds do not break. What breaks are hydrogen bonds. So that's our answer to question 14. Move on to question 15. Choose the statement that is correct in relation to isomerism in monosaccharides. In relation to isomerism in monosaccharides. So the best you can do here is, let's have monosaccharides. So you know that we have glucose, we have galactose, then lastly we have fructose. These are the most discussed monosaccharides. So isomerism, these are molecules that have got the same chemical formula but different the arrangement of electrons in space. That is what we call isomer. So all these are monosaccharides with a 6 carbon, and their chemical formula is C6 H12 or 6. All of them have got this chemical formula, but they are different in terms of how these atoms are arranged. So I've got two types of isomers there which you should appreciate. We have what we call structural isomers. Then we also have got what we call stereoisomers. Okay. So structural isomers, these are isomers which come as a result of the functional groups being at a different position. So we know that the functional group in carbohydrates is a carbonyl group. So depending on the position, you know that for galactose and glucose, this carbonyl group is at carbon 1. It is at carbon 1. Whereas in fructose, this carbonyl group can be at any other position. Mostly it's carbon 2. So this difference between the arrangement of this functional group in glucose and fructose, these type of isomers are what we call structural isomers. So glucose and fructose are structural isomers. Why? It's because the position of this functional group is at different positions in these two monomers. Then we also have got what are known as stereoisomers. So stereoisomers, these are isomers that have got the same, that the functional group occupies the same position, but the arrangement of these other atoms at a particular position is different. So stereoisomers, we have got glucose and galactose. Glucose and galactose, these are stereoisomers of each other. So the functional group, which is a carbonyl group, for both of them it is at carbon 1. That means they are aldose. They are both aldose sugars, whereas fructose is ketone. I didn't mention earlier. Is ketone because the position of carbonyl group is not at carbon 1 for fructose. So we are saying that glucose and galactose, these are stereoisomers of each other. So they differ in the arrangement of atoms at carbon 4. So at carbon 4, what we are going to observe is that one of them has got OH group this side and hydrogen this side. The other one has got OH group this side and hydrogen the other side. So they differ at carbon 4, that is glucose and galactose. Hence they are known as stereoisomers. Stereoisomers are also known as epimers. So it's as good as us saying galactose and glucose are epimers. So the difference exists at carbon 4. It's not in terms of the functional group, but just the atoms. They are on different positions. So let's go back and answer this question. So choose the statement that is correct in relation to isomers of monosaccharides. So D and L galactose are still structural isomers of each other. So structural isomers, the position of the functional group has to be on different carbon. So both D and L, they have got the functional group at carbon 1, so they can't be called structural isomers. Glucose and fructose are optical isomers of each other. That is the mirror images of each other. This is false. Alpha glucose and beta galactose are stereoisomers of each other. Yes, this sounds somehow true. The open chain and ring form of glucose are optical isomers of each other. This is false. Then galactose and fructose are stereoisomers of each other. So galactose and fructose, they also differ due to the position of this group. So such isomers are what we call structural and not stereo. So this is a false statement. So the correct answer here is going to be option 4. The open chain and ring, no, option 3. Alpha glucose and beta galactose are stereoisomers of each other. So glucose and galactose are stereoisomers of each other because they differ in terms of the arrangement of atoms at carbon 4. The other one is like this, then the other one is like this. So that's our answer there. That's our answer. Later on, I'll also explain what beta and alpha simply means. How do you determine that a particular monosaccharide is alpha or beta? So choose the statement that is correct in relation to the ring formation of monosaccharides. So ring formation, I'll be quick here to do this. So we have got two types of rings which are formed. We have the 6-sided ring and the 5-sided ring. So the 6-sided ring is formed by glucose and galactose. So this ring here, which we have here, has got 6 sides: 1, 2, 3, 4, 5, 6. This ring is what we call pyranose. So this is a pyranose ring. 6-sided ring is pyranose ring, and this can either be glucose or galactose. So only glucose or galactose will form a pyranose ring. Then we also have got a 5-sided ring. So a 5-sided ring, we can't call it as a pyranose ring. A 5-sided ring will look like this. Okay, so a 5-sided ring, you have something like this. So if you count these sides, you're going to find that they are just 5. So you have 1, 2, 3, 4, 5. So you are supposed to have, you also have got 6 carbons. So carbon 6 is at this position. So this is going to be the 6th carbon. But the ring itself only has got 5 sides. So this ring is what we call a furanose ring. So fructose and pentose sugars are the ones which form this ring. So this is a furanose ring. It's formed by fructose as a monosaccharide. So choose the statement that is correct in relation to the ring formation in monosaccharides and how this come about, how the the ring comes about, because that's what I can see this question is asking us. So I've got 6 carbons. Okay, so 6 carbon, 1 2 3 4 5 6. So what happens is that in glucose and galactose, where they form pyranose ring, you have this is going to be carbonyl carbon. So this carbon 2 is going to attack carbon 1 is going to attack carbon 5, thereby bringing about this pyranose ring. Whereas in fructose, that carbonyl group is at carbon 2. So it's carbon 2 which is going to attack carbon 5 to bring about pyranose ring. So choose the statement that is correct in relation to the ring formation of monosaccharides. So carbon 4 combines with carbon 1 or the ribose open chain to form a pyranose ring. So carbon 4 combines with carbon 1 to form an open chain. Carbon 4 combines with carbon 1 or the ribose open chain to form a pyranose ring. So ribose, this is going to form a pyranose ring. So carbon 4 combines with carbon 1 or the glucose open chain to form a pyranose. So glucose will form a pyranose. So I'm disqualifying not on just based on the carbon and whatever, just the ring itself. So carbon 2 combines with carbon 1 or the galactose open chain to form a pyranose ring. Pyranose ring, yes, this is true. Galactose is going to form a pyranose ring, but it has to be carbon 4. So in this case, 1 2 3 4 5 6. So instead of 5 here they have used the 4. So it has to be carbon 1 which has got carbonyl group for glucose or galactose to attack carbon 4. So carbon 4 is going to be this one here. So it will form a pyranose ring. So they have used carbon 4 here. I also respect this. So it has to be carbon 1 which has got this functional group will attack carbon 4 of galactose, then it will form a pyranose ring. Then it is, that was option. So this is false because of this. So it's a false statement, but it's true this other side. Carbon 4 combines with carbon 1 or the fructose. So this has to be carbon 4 combines with carbon 2. This was supposed to be 2. Why 2? It's because in fructose that carbonyl group is at carbon 2. So it's the carbon which has carbonyl group that will attack carbon 4. Then 4 is saying carbon 4 combines with carbon 1 or the deoxyribose open chain to form a pyranose ring. So pyranose ring, as we have already said, a pyranose ring will be formed. Okay, so deoxyribose is as far as I'm concerned, I think deoxyribose is an aldose, it's not a ketone. So if deoxyribose is a ketone, this is going to be a true statement. Deoxyribose is going to form a pyranose ring, and the carbon 1, that is the carbon which contains carbonyl group, is going to attack carbon 4. Thereby bring about pyranose ring. So we'll go with option 4, but I'm not certain. Let me just quickly go back to confirm. Carbon 4 combines with carbon 1 of ribose open chain to form a pyranose ring. So ribose has got 5 carbons, so it can't form a pyranose. It will form a pyranose. Then carbon 4 combines with carbon 1 of glucose open chain to form a pyranose. So this is first because of this. Glucose will form a pyranose. Then carbon 2 combines with carbon 1 of galactose open chain to form a pyranose ring. So carbon 2 combines with carbon 1? No. It has to be carbon 1 and carbon 4. Then carbon 4 combines with carbon 1 of fructose to open chain to form. So this first because of that. So I think option 4 or 5 will qualify. That's it, but you can also look it up. The formula this represents. So this is a carbohydrates with 3 carbons. So which of these has got 3 carbons in it? So disaccharide, no. Disaccharide does not respect this formula because that is a CH2O then N. So N in that case was just 3. So C3H6O3. Disaccharide do not respect this formula. So that it can't be disaccharide. Hex was sugar, so hex simply means 6. So N was supposed to be 6 for it to be hexose. So false. The glyceraldehyde has got 3 carbons. So if you substitute N with 3, you're going to get this. So yeah, this is true. Deoxyribose. So deoxyribose is a pentose sugar, has got 5 carbons, and it has got less hydrogen. It has got less than 1 hydrogen from the maximum. So it was supposed to be C5H9 then O5. Then fructose. Fructose is a pentose, is a hexose sugar. It has got 6 carbons, so it was supposed to be C6 H12O6. So the answer is 3. Glyceraldehyde is the one which has got 3 carbons in it. Substitute N with 3, you are going to get that chemical formula. Which one of the following molecules is used for the synthesis of nucleic acid? So the sugar that is used in nucleic acid is what we call a pentose sugar. So pentose sugars, these are 5 carbon sugars. So disaccharides, oligosaccharides, polysaccharides, deoxyribose, pentose. So the answer is pentose. So I have deoxyribose and ribose sugar. Question 19. Start the structure A, B, and C, and then choose the option that gives the correct image between the structure and its name. So are these structures. So first of all, let's just focus on the position of the functional group. Let's focus on the position of the functional group. So we have a functional group at position 1. This functional group is that group which we've been referring to, the carbonyl group. So for all the 3, they have got carbonyl group at carbon 1. They have got carbonyl group at carbon 1, which means that all of them are aldose sugars. So in the first place, we don't have ketone, we just have ribose. Then now let's count the total number of carbons. This one has got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So C is giving us a hint here. So C has got 5 carbon. Because it has got 5 carbons, this is going to be a pentose sugar. Pentose sugar. So pentose sugar can either be ribose or deoxyribose. Deoxyribose. But deoxyribose should have a shortage of hydrogen at carbon 2. So we check carbon 2. So carbon 2 is here. So carbon 2 has got maximum number of hydrogen. So this can't be deoxyribose. Automatically it's a ribose. So C has to be ribose. Then I can see, now what we have here, all these are open chain structures. Now there is what we call alpha and beta, then also D and L. So open chain structures, most of the time they help you to tell if a particular sugar is either D or it's L form. So a D form, I'll start with a D. So D is going to have the OH group on the carbon next to the terminal carbon to your right. So we have this carbon, this is the 6th carbon or the last carbon. Here this is the last carbon, this is the last carbon. So the carbon just before this last carbon is the one we should check. In this case we're going to check this one. Then the position of this hydroxyl group. If it is to your right, to your right, this is going to be a D. If this group at this carbon is to the left, that is L. So this is going to be a D ribose sugar. Then this one is going to be okay, you check this one, not that one, where I was going. So this one is also a D. Then this one, the hydroxyl group next to the terminal carbon is to the left. So this is L. So one thing is clear, it's out. Okay, then now our focus should be on A and B. So A and B, we can see that all of them have got 6 carbon in them, but the position or the arrangement of these atoms is different. So what are these going to be? Of course, here we're supposed to have galactose and glucose. So galactose, I'll start with D-glucose. So D-glucose, you're going to have, of course, on carbon 1, you're going to have this group and hydrogen. Then on carbon 2, 3, 4, 5, and the last one. So D-glucose, which is the normal one, has got OH group here, another OH group here, then OH group here, OH group there. Then down here you're going to have CH2OH. Then here you just add these hydrogen. Then check carbon 4. So on carbon 4, which is which one here? So carbon 4, 1, 2, 3, 4. Here. This is where glucose differs from galactose. Galactose has got this group to the left. So 1, 2, 3, 4. So carbon 4 is this one here. So here the OH group is to the left there. So this automatically has to be galactose. This has to be galactose. Then for this one is going to be glucose, but it's not the D. It's not this one which you see that I've drawn here. It's going to be the L. So L is different from this. On carbon 2, you're going to find that this group is to the other side, hydrogen is the one which is on the other side, this one here. Then also, the hydroxyl group on the preceding carbon to the terminal carbon is to the left here, as you can see. So this is L-glucose. So this has to be L-glucose, this has to be D, or the second one has to be D-galactose, then this one has to be D-ribose. Do we have something like that on the options given here? So we have alpha glucose, beta glucose, beta ribose. So I said that for you to tell if it's going to be beta or alpha, this one is much you are easy to tell when you have a ring. A ring is very easy for you to tell if it's alpha or beta. But in this case we have open. So open chain structure is going to help us to tell if it's D or L. So we are not going to focus on alpha and beta, but D and L. Beta glucose, L what. So we have said that C should be our guide. So C, we should get a D ribose. We should get D ribose. So D ribose, we have option 3. Structure B is saying D galactose. So D galactose, yes. Then one is saying L glucose. So L glucose, yes. So the answer here has to be option 3. Quite tricky, but very simple. So that's how you would have handled this question. So the answer was option 3. Hope you have also learned something different or something new. Identify the carbon with a polar bond in dihydroacetone. Identify the carbon with a polar bond in dihydroacetone. So dihydroacetone has got, I think dihydroacetone has got 4 carbons. So in these 4 carbons we have so in these 4 carbons we are looking for the carbon which has got a polar bond. A carbon which has got a polar bond. Dihydroacetone. Does it have 3? Dihydroacetone. So identify the carbon with a polar bond in dihydroacetone. So dihydroacetone has got 3 carbons, not 4. So it has got 3 carbons. So because it has got 3 carbons, the carbon with a polar bond, that is the one which has got this group, it's carbon 2. So the answer has to be 2. Identify the carbon with a polar bond in the hydroacetone. So the answer has to be carbon 2 because it originally got 3. So it has got this group at carbon 3. So that's the polar bond. Choose the statement that is correct in relation to the structure of disaccharides. So disaccharides, we have lactose, we have maltose, and we have sucrose. Then you should also be able to know the type of bond that you're going to find in each of these. Here you're going to have beta 1 to 4. So this is beta 1 to 4. In maltose you have alpha 1 to 4. Then in sucrose you have beta 1 to 2. Okay? Even though sucrose is made up between alpha glucose and beta fructose, so the bond is supposed to be alpha beta 1 to 2, but we usually call it as beta 1 to 2 glycosidic bond. So choose the statement that is correct in relation to the structure of disaccharides. Maltose is composed of beta glucose and alpha glucose. So maltose, they are all alpha glucose units. So this is false. Then 2 is saying sucrose has a glycosidic bond between carbon 1 of glucose and carbon 4 of fructose. So it has a glycosidic bond between carbon 1 of glucose and carbon 2 of fructose. Then lactose is composed of 2 alpha glucose molecules, so it's 2 beta glucose molecules. Sucrose is composed of alpha glucose and beta fructose. This is this is true. This is what I was explaining here. Sucrose is made up between alpha glucose and beta fructose, so the bond is alpha beta 1 to 2. But I was saying that most of the times you find that the books will call this bond as beta glycosidic bond. Maltose is composed of alpha glucose and beta fructose. So maltose is just an alpha glucose unit. So the answer here is option 4. Sucrose is composed of alpha glucose and beta fructose through a 1 to 2 glycosidic bond. Choose the correct statement. Maltose is a non-reducing sugar because of the 1 to 2 glycosidic bond. So all the disaccharides that I listed earlier, only sucrose amongst those is a non-reducing sugar. The reason why it's a non-reducing sugar because both groups in glucose and fructose, this group is involved in the bond formation. So there is no free group that can react with or that can reduce copper 2 sulfate. So hence it's a non-reducing sugar because of this bond. So maltose is a non-reducing sugar because of 1 to 2 glycosidic bond. This is true. Sucrose is a reducing sugar. The moment you say that sucrose is a reducing sugar, this is a false. Lactose is a non-reducing sugar. Lactose is a reducing sugar. Because one of its monomers, this group is free, so it's able to react. Sucrose is a non-reducing sugar because of its 1 to 2 glycosidic bond. Sorry, this was maltose. So maltose is maltose is a reducing sugar. I thought this was a sucrose. Sorry, so this is false. Sucrose is a non-reducing sugar because of its 1 to 2 glycosidic bond. Yes. In maltose, it is a 1 to 4 glycosidic bond. Thereby, it means that this bond, one of its monomers, this group is free, so it's able to react. That's why it is a reducing sugar. Then option 1 and 2 are correct. No. Option 2 is false, option 1 is false as well. So the correct statement here is option 4. Sucrose is a non-reducing sugar because of 1 to 2 glycosidic bond. As long as a particular disaccharide has got a 1 to 4 glycosidic bond, that is a reducing sugar. As long as a particular disaccharide doesn't have this bond, it is a non-reducing sugar. So on I've got a sucrose which has got 1 to 2. 1 to 2 mean that both carbonyl groups in both monomers are involved in this bond formation. So there's nothing like to react with copper. The most suitable molecule for translocation of carbohydrates in plants is so the most suitable molecule of translocation, that is the movement of carbohydrates in plants, is so for storage. So you know that carbohydrates in plants, it has to be stored. before it is stored, it has to be transported. So it is transported and stored in form of what? In starch. So carbohydrate is stored and transported in plants in form of starch, whereas in humans and animals, it is humans or animals, it is stored and transported in form of glycogen. In form of glycogen. So the answer has to be starch. And the starch, you know that we've got two types. There is a amylose, which is linear. We also have got amylopectin, which is branched. Amylopectin, which is branched. But they're both types of starch. So we have the most suitable molecule, that is option 5. So it's starch. Cellulose, this is a structural component. Starch, carbohydrates are not stored in form of cellulose. They are stored in form of starch and transported in form of starch, not cellulose. This is just involved in structural components. Milk sugar is made from, milk sugar is made from maltose and fructose, sucrose and galactose, glucose and fructose, glucose and galactose, galactose and galactose. So milk is come from lactose. So lactose is made up of galactose plus glucose. So the answer has to be the one with glucose and galactose, or the other way around. Glucose and galactose. So option 4. So that is milk. Milk is lactose. Lactose is made up of those two units because it's a disaccharide. Choose the correct statement. Branching is important in the function of structural polysaccharides. So structural polysaccharide, here we are talking about cellulose. Cellulose is not branched, so that is the first statement. An energy storage polysaccharide should be fibrous in nature. So fibrous simply means that it has to be more compact and short. It has to be more compact and short. We have fibrous and I've forgotten the other one. I'll mention it later. So fibrous simply means that it has to be more compact and short. And energy storage polysaccharide should be fibrous in nature. That is somehow true. Amylopectin is highly branched and hence more difficult to digest than cellulose. So amylopectin is highly branched, that is true, but it is not more difficult to digest than cellulose. Cellulose is very difficult to digest as compared to amylopectin. The structure of glycogen is similar to that of amylopectin. Yes, this is a true statement. In which way are these two similar? So if you look at amylopectin has got two bonds. You have got alpha 1 to 4 and also have got alpha 1 to 6. So alpha 1 to 6 exists where the branch is. So the same is glycogen. Glycogen also got alpha 1 to 4 and alpha 1 to 6. But the difference is on how these branches come. So in amylopectin, this branch, the 1 to 6, comes every after 24 to 30 units. Whereas in glycogen, that branch will come every after 8 to 12 units. Which simply means that glycogen is more branched than amylopectin. But they are similar for the fact that they both contain alpha glucose as their unit. Then they both have got 1 to 4 and 1 to 6 glycosidic bond. So this is a true statement. Then amylose gives a blue-black color with iodine solution. So this simply means that you know that when you are testing for starch, this is the indicator that there is starch. If a particular solution is able to turn blue-black when you react it with iodine, it means that starch is present. So amylose is defining starch here. Amylose is component of starch because we have amylopectin and amylose. So that's starch. So it's able to turn blue-black. Because it's starch, it just has to turn blue-black when you react with the iodine solution. Now this question is quite confusing because they say choose the correct statement. So if I look at this one is correct, this one is also correct. 3 is false. An energy storage polysaccharide should be fibrous in nature. No. Fibrous, yes. fibrous, it has to be more compact. Yeah, this is also somehow true. Branching is important in the function of structural component. This is false. So, choose the correct statement. I'll leave it here. I'll leave it on option 4 and 5. Option 4 and 5, they are very correct with regards to this question. So, I don't know which one they were marking here, but both 4 and 5 are correct. And we don't have an option which combine the two. So I think any of these was being marked as correct, as a correct option. So choose the correct statement. 26. Amylose has alpha 1 to 4. So let's start. Amylose, we said that this is linear. It has got alpha 1 to 4 glycosidic bond. Then we also have got amylopectin. Amylopectin is branched. Amylopectin is branched, so it has got alpha 1 to 4 and also alpha 1 to 6. There's no beta. So amylose has alpha 1 to 4, yes, beta 1 to 4 glycosidic bond. So it's false because of this part. Amylopectin only has got alpha 1 to 4. Or amylose. Amylopectin has alpha 1 to 4, yes, beta 1 to 6 glycosidic bond. So this is also alpha. The 1 to 6 is also alpha, it's not beta. Then cellulose has alpha 1 to 4 and beta 1 to 4 glycosidic bond. Cellulose has got, it's linear as well, but it only has got beta 1 to 4. There's no alpha there. So it's false because of this. Then 4 is saying amylose has alpha 1 to 4, yes, beta 1 to 6 glycosidic bond. So amylose only has got a single type of glycosidic bond, that is alpha 1 to 4. This is false. Then 5 is saying amylose has alpha 1 to 6 glycosidic bond. So this is also false. Amylose has alpha 1 to 4 glycosidic bond. So this question has no answer. The closest was, if this one was changed, option 5, if it was changed to alpha 1 to 4 glycosidic bond, it would be the correct answer. But the way we have these options here, there's no option which is correct. So I would leave it blank or put option 6 because I don't see an answer here. If nothing was talked about or was discussed in an exam on this question, then I would have put option 6. But it's better off, like in an exam, if you observe that a particular question is not correctly asked, it's better you raise your hand and ask. So if they tell you to say that the answer is there, that's when now you can start thinking in those areas that I can't still see the answer here, so you put option 6. The complete hydrolysis of amylopectin yields. So amylopectin is a starch which is made up of alpha 1 to 4 and alpha 1 to 6. So when you hydrolyze, that is, you are adding water, so you are breaking it down. So what are you going to yield? So you are going to yield alpha glucose, because amylopectin has got monomers which are alpha glucose. So when you add water, you are breaking down that polysaccharide, then you are going to have alpha glucose units. So a complete hydrolysis of amylopectin yields amylose, galactose, glucose, fructose, starch. So you yield glucose, which are just the monomers. Then 28. Choose which of the following statement is true. Polysaccharides are chemical reactive substances. Polysaccharides are chemical reactive substances. So by chemical reactive here, we are saying that they are reducing sugars, which is false. They are chemical and reactive substances. Why? It's because all of these groups are taken up. So there is there's no free group that is able to react. So they are chemical and reactive. Amylose is starch. Yes, this is true. Carbon 1 is the asymmetric carbon in glucose. No? So asymmetric carbon, we said that it has to be linked to 4 different groups or atoms. So carbon 1 of glucose is only linked to 3. This is carbon 1. This is how it looks like, carbon 1 of glucose. So it can't be called an asymmetric carbon. It's not linked to 4 different groups. Then starch, glycogen, and cellulose are oligosaccharides. So oligosaccharides, these are polysaccharides which have got carbons ranging between 3 to at least 10. So if you look at starch, starch has got a lot of units going beyond 10, so it can't be called oligosaccharide. So it's glycogen and cellulose. These have got a lot of units going beyond 10, so they are not oligosaccharides. Sucrose has its asymmetric carbon free for further chemical reactions. So earlier we said that sucrose is a non-reducing sugar because its carbonyl carbon is not free, so it cannot undergo further chemical reaction. So that is false. So the correct statement here is option 2, which is saying amylose is a starch. Yes. So also we have got two types of starch, amylose which is unbranched and amylopectin which is branched. The hydrolysis of lipids produces. So if you add water to a lipid, what are you going to use? So let's consider triglyceride. Triglyceride is made up of a glycerol. This glycerol is linked to three fatty acids. So when you through an ester linkage. So when you add water, what you're going to have, you're going to use these fatty acids and glycerol. So the hydrolysis of lipids produces glucose, no. Glycerol, yes. Fatty acids, yes. Amino acids, no. So 5 is saying 2 and 3. So glycerol and fatty acids. So the answer is going to be option 5. So when you add water to a lipid, you're going to use glycerol and fatty acids. How many electrons are there in the third shell of an atom with atomic number of 23? How many electrons are there in the third shell? So 23 is going to be 2, 8. So 8 plus 8, that is 16. 16 plus 2, 18. So for us to get to 23, that is 18, 19, 20, 21, 22, 23. So we're going to have 5. So the question was, how many electrons are there in the third? So the key term is third. So the third shell is this one here. How many electrons? 8. So the answer has to be 8. But the valence electron number is 5. And the valence number is going to be 3. You know how to deal with those, I explained earlier. The number of electrons in the highest energy level of calcium, atomic number is 2, the number of electrons in the highest energy level. So the outermost shells are going to be, so we're going to have 2, 8. 2 plus 8, that is 10. For us to get to 20, we have 10 more, so another 8, then that is 18, then 2. So these are going to be electrons in the outermost shell, so they are just 2. The number of electrons in the highest energy level of calcium, atomic number of this is going to be 2. Why is that the case? It's because the energy increases as you move away from the nucleus. So electrons which are far away from the nucleus, they have got high energy. So the farthest electrons in this atom are going to be these ones, 2 electrons which will be in the outermost shell. So the answer is 2. The closer the electron is to the nucleus, the less the energy. Water is liquid at room temperature because of dash of water. So why water is a liquid at room temperature? Because water has a high boiling point. This is true. Water boils at 100 degrees Celsius. So room temperature, we're talking about 25 degrees Celsius, which means that this temperature is less as compared to this. So it will exist as liquid. Then, because of high melting point, water melts at 0 degrees Celsius. So this was supposed to lead because of low melting point. So because of low melting point, we have got a room temperature is 25. So 25 is quite large, higher as compared to 0 degrees Celsius. So it's liquid because of low melting point, not high. The high heat of vaporization, quite alright, water has got high heat of vaporization, that is the energy which is required for water to change from liquid to gas, but does not contribute to why water is liquid at room temperature. Because of adhesive forces, no, both 1 and 2. So 1, we said 1 is correct because of high boiling point. Then 2 was saying because of high melting point. So this was going to be true if this was reading because of low melting point. So the only correct answer here is option 1. Option 2 is false. So that's the answer. Water is liquid at room temperature because it has got a high melting point or boiling point. It boils at 100 degrees Celsius. So room temperature cannot change the state of water. Polar molecules can readily dissolve in water because they have got charges. So polar molecules can readily dissolve in water because polar molecules can form hydrogen bonds with water. Polar molecules can replace water-water interactions with more energy provided. No. Water can interact with charged solute molecules. Yes, this is true. All molecules form solutions with water. All molecules form solutions with water. Both options 1 and 3. So all molecules form solutions with water. This is false. Cooking oil can't form a solution with water. Something has to dissolve in water for you to have solution. So we have some molecules which cannot dissolve in water, so you can't have a solution. So this is false. Water can interact with charged solutes. This is true. Like sodium chloride. This is able to interact with water, thereby be able to dissolve. Then also option 1 is saying polar molecules can form hydrogen bonds with water. Polar molecules can form hydrogen bonds with water. It's also somehow true, but it's not always that water will form hydrogen bonds with polar molecules. So option 5 is combining both options 1 and 3. I think this will be the best option, option 5. So we'll go with option 5. 34. The most important reason for the unique shape of water is so earlier on I said water initially was supposed to be linear like this. Now because of the lone pairs which are able to push each other, they are forcing this hydrogen to create this shape. So this question is talking about this shape. The most important reason for the unique shape of water is the covalent bond pattern in water molecules. So not really. The bond angle between the two hydrogen atoms in water, the presence of a lone pair of electrons in water, that water can be ionized at room temperature. Yes, so water can be ionized at room temperature, though it's very low. So we are going to have this plus this. Then this will be like this. So it will be ionized. Ionized meaning that it's reversible. You have something like this. So this is true. Presence of lone pair. This one, yes, is able to push this hydrogen inwards. Then the bond angle between two hydrogen atoms, yes. So this bond angle is what brings about the bent shape. Then the covalent bond pattern in water molecules. So the covalent bond pattern in water molecules, which is this one. To some extent, all this contributes to the unique shape of water. So we'll go for option 5. All the options above are correct. So the question was not quite specific. So each one of these contributes in some way to why water has got a unique shape. So we have hydrogen bonds can be expected to form only between hydrogen and so we said hydrogen bonds can be expected to form when hydrogen is reacting with either oxygen, nitrogen, or fluorine. So this will be a hydrogen bond. So hydrogen bonds can be expected to form only between hydrogen and carbon, no, hydrogen. Hydrogen, that's not a hydrogen bond, no. Oxygen, nitrogen, yes. So option 3 and 4. 3 oxygen, 4 nitrogen. So the answer is option 5. If that was also fluorine was also going to be the answer. Not chlorine, but fluorine. Adhesive forces lead to which of the following? Adhesive forces lead to dash which of the process through which water is absorbed into roots of plant. So adhesive forces lead to capillary action or capillarity. We talked about this area. Adhesive forces lead to surface tension, no, polarity, formation of a tough film of water, elasticity of water, capillary action. So adhesive forces lead to capillary action, which is the process through which water is absorbed into roots of plants. So water is able to move against gravity because of capillary action. And capillary action area, I said that it's achieved by cohesive forces and adhesive forces. So here they have defined for us, and they have only given us, they have defined for us what capillary action is. So that's the answer. That's the answer. Then which one of the following represents functional groups in carbohydrates? So in carbohydrates, you're going to find hydroxyl group, you're going to find this carbonyl group, but again, depending on the position of this carbonyl group, you can either have a ketone or an aldose. So these are also known as alcohols. Which of the following statement represents functional groups in carbohydrates? So alcohol and the carboxyl group. So carbonyl and carboxyl are not the same. Carbonyl group is this group, carboxyl group is this group. So we don't have this group in carbohydrates. We only have got carbonyl group. Aldehyde and ketones, aldehyde and ketones is referring to this group, now just the position. If this group is at carbon 1, then it's aldehyde. If it's at carbon, any of the carbon, not the first or last, then it's a ketone. Hydroxyl and hydrogen groups. So hydrogen is not a functional group. Carboxyl and amine. So this, carbon and hydrogen, these are not functional groups. So the functional groups here are going to be carbon 2. Oh, it's going to be option 2. Aldehyde and ketone. So these are just referring to carbonyl group. So carbonyl group, these are the functional groups in carbohydrates. So depending on the position of this one, it can either be aldehyde if it is at carbon 1, or it can be a ketone if it is at any other carbon. So we have seen that fructose has got a ketone, whereas galactose and glucose have got aldose. So the answer is going to be aldehyde and ketone. That is referring to a carbonyl group. Which of the following is true? Is a true statement about glucose. So it is used for storage of energy. Yes, glucose is used for storage of energy. It has 4 asymmetric carbons, no? That it has got 4 carbons which are linked to 4. I think it only has got 2, which are linked to 4 different functional groups or atoms. It is stored as starch in animals, no? So it is stored as glycogen in animals. It is stored as starch in plants. It has 6 asymmetric carbon. No, we said it only has got 2. It is oxidized to form fructose. No, it can't be oxidized to form fructose. So the only answer here, it is used as a storage of energy. So the answer is option 1. 39. 39 reads, which one of the following is a carbohydrate with 6 carbon atoms and a ketone group, a ketone as its functional group? So which one of the following is a carbon with 6 carbon? So 6 carbon, we have got glucose, galactose, and fructose. So glucose and galactose have got an aldose or aldehyde functional groups. So it is only fructose which has got 6 carbon and it has got a ketone as its functional group. So the answer is fructose. The answer is fructose there. Question 40. Question 40 reads, choose the correct statement or statements. So collagen is a globular protein consisting of 3 polypeptide chains. So collagen, indeed, it contains 3 polypeptide chains, but it's not globular, it's fibrous. That it's more compact and short. Globular is something which is long. So something which is long, and if we look at collagen has got 3 polypeptide chains, and these polypeptide chains, they are long. So we can't say collagen is globular. Globular is something that is compact and short. So it is long. So it is not globular. So it's false because of this. It was supposed to be fibrous. Then 2 is saying the beta-pleated sheet is found in a fibrous proteins. So beta-pleated sheet is found in fibrous proteins such as Beta-pleated sheets are found in secondary structure of protein, and an example can be silk. In silk, you are going to find a beta-pleated sheet, and silk is a fibrous protein. So this is a true statement. Hemoglobin is a fibrous protein with a quaternary structure. So if we look at hemoglobin is compact. It's not long. Something fibrous is something that is long. Okay? So it has to be linear, very long. But if you look at hemoglobin, it's compact. So it is not fibrous, it's globular. And it has got a protein with a quaternary structure. So it is false because of this. It was supposed to be globular here. Statements 1 and 3. So 1 is false already because of this. Then 3 is false as well because of this. Then statements 2 and 3. So already 3 has been disqualified because of fibrous. Hemoglobin is globular. It is more compact and short, and not fibrous. It's not long and no, it's not long. But it's true. It has got a quaternary structure. So the only correct option here, or the correct answer to this question, is option 2. The beta-pleated sheet is found in a fibrous protein such as, I've given you an example, such as silk.